Now, using the same approaches as we used in the previous questions, we can now turn to formulas and literal equations. The difference here is that we may or may not have any numerical values, but we certainly have a lot of variables. In this particular equation, we're being asked to solve for the lowercase p. We have to be a little bit cautious. We have an uppercase p, lowercase n, lowercase p, and lowercase I. We have to be careful not to confuse, in particular, the two p's. There are two very good approaches we can use for these, and I'll show them to you separately. There are times when one approach is better than the other, but for this one, it actually doesn't matter. But let's start with exactly the same approach that we used for all previous examples of solving equations. And that was to start with distributive property. Why? Because we want to open up any groupings, get rid of any fractions, get rid of any brackets. In this case, we have brackets, we get rid of them by using the distributive property. So we have capital P is equal to NP minus NI. Where's the variable we're trying to isolate? It's in this term. So now we'll isolate the term that our variable is in. To get rid of the negative Ni, we'll add Ni to both sides. So we have P plus Ni is equal to NP. P's last remaining problem is that it's being multiplied by n, so to eliminate the n, we divide both sides by n. Be careful to divide both of the terms on the left-hand side by n. So these cancel, and we have P, I'll just write it on the left-hand side here, is equal to capital P plus Ni, all divided by n. And that's a perfectly fine answer. Now maybe you're already seeing what's maybe a little bit of a shortcut compared to what we just did. Again, we recognize that our lowercase p is here, and that's the one we'd like to isolate. Let me write the equation again. P equals n times lowercase p minus lowercase I. And first I notice that there's only one instance of the p. So we don't have to pull together different terms that have p's in them. And it has a coefficient of 1 inside these brackets. So if we could just identify, start. It has a coefficient of 1 within these brackets. So if we could just isolate the brackets, we'd be well on our way to having that p isolated. So how do we isolate the brackets? Well, we get rid of the n, and the n is being multiplied by the brackets, so getting rid of it means dividing both sides by this lowercase n. So now we have uppercase p over n is equal to lowercase p minus I. Here's the term with the p in it. It's in fact the only thing in that term. So to move the I over, we simply add I to both sides. I'll rewrite it in the other direction. So I have lowercase p is equal to capital P over n plus I, because I've added plus I to both sides. These are both perfectly good answers. In fact, I hope you can recognize that they're equivalent. I can think of adding these two fractions. To add the two fractions, they need a common denominator, so I'd have to turn I into a fraction over n, which I would do by rewriting I as in, or ni if I want to make it match what's on the left-hand side exactly, and then add those two. Similarly, I could take this piece and say, well, I know that I have one term on the bottom, but I have two terms on the top, so I can't just cross out the ends. I can't cancel my terms, but because I only have one term on the bottom, I could rewrite this as two separate terms. P over n plus ni over n. And then I can cancel the ends. So that gives me p over n plus I. So the two roots are identical. The answers are equivalent, and it is absolutely okay here to leave your answer in this form or in this form. They're both easy to understand. They're both easy to manipulate further. We have no complex fractions, fractions within fractions. So for this problem, either works well. And in fact, I would probably personally choose the method on the right. It took me slightly fewer steps to get to the final answer. This question has similarities to our last one. Here we're told that capital W is equal to capital L times omega L, that's the little W looking thing, plus 2 times P, all divided by 8. And we're instructed to isolate P. So again, that's the variable, one of the variables inside the brackets. Couple differences here. Obviously, we have a fraction on the right-hand side, and secondly, the P has a coefficient other than 1. So that's going to change how our grouping or ungrouping steps will work. Okay, stepping back and looking at this problem for a moment, looks like undoing groupings is a great idea, and the grouping I'm thinking about is the fraction. Let's get rid of that 8, and then we'll talk about the groupings that are the brackets in the numerator. So to get rid of the 8, we're going to multiply both sides by 8. It's a bit messy, let me rewrite that. So we have 8 times W on the left-hand side. On the right-hand side, the 8's will cancel, so we'll have L times omega L plus 2 times P. Keep an eye on the variable we'd like to isolate. We'll try this next step 2 different ways. We'll do the same thing that we did in the last one to start. So we'll use distributive property to undo the groupings on the right-hand side. So that gives us 8 times W is equal to omega L squared, as we take L and multiply it by omega L, plus 2LP. I've chosen to put the variables in alphabetical order here, but the Greek symbols out front. Okay, now we've isolated P to some extent in that we've already isolated the term that the P appears in. So all we have to do is remove the other term from this right-hand side, and we'll do that by subtracting omega L squared from both sides. So we end up with 8W minus omega L squared is equal to 2LP. 2 and L are being multiplied by P, so to move them to the other side, we'll divide both sides by L and 2. The 2's divide and cancel, the L's cancel, and I'll write P on the left-hand side here, but that's equal to 8W minus omega L squared all over 2L. And that's a pretty solid final answer. Again, if you like, because I have 2 terms in the top but only 1 in the bottom, you could rewrite this as 2 fractions, and in the second fraction you'd be able to cancel the L's, but there's really no need to, as this is already pretty tidy. So that's one approach. But what about the second approach that we tried on the previous slide? We noticed that there's only the one instance of the P, and it's inside the brackets, so we could isolate the brackets first. And we would do that by dividing both sides by L. So we'd have 8W, we just rewrite the entire thing and then show the division there, 8W over L, and the L's would cancel on the right-hand side. So we have 8W over L is equal to omega L plus 2P. So far, so good. Similar to the last technique, where we had 2LP, now we have 2P. So we only have one term with the P, and we can isolate that term by subtracting omega L from both sides. So we've got 8W over L minus omega L is equal to 2P. This is where we run into some problems, though. Sure, we can isolate the P by dividing both sides by 2, and I'll absolutely do that. So the 2's will cancel. So we have all of this is equal to P. It's correct, but we don't like the fact that it's got a complex fraction in our answer. Right? So we have a fraction in the numerator of a fraction. We work through how to resolve complex fractions or how to rewrite them, how to say this as division for a reason. Complex fractions are difficult to read. So we want to leave our answer so that it's not a complex fraction. You know how to do that. You know you can change this to division by 2 rather than using, so division using the division symbol rather than using the fraction line. And then you do the division by changing division to multiplication by the reciprocal. And then at least we're well on our way to rewriting this. And you should be able to rewrite the expression on the right so that it matches this expression on the left. You can avoid all of this by simply undoing all groupings first, getting rid of the fraction, and then also opening up the brackets. The difference between this question and the last one is that the p in the original question has a coefficient of 2, where previously there was a coefficient of just 1. Here we've got a formula that relates volume and temperature. Careful here, we've got V and V naught. V with the subscript 0 is called V naught, as well as T and T naught. As soon as a variable has a subscript, we have two different variables. So when we're told to solve for T, we're specifically being asked to solve for this variable. We've got a lot going on here in terms of brackets. Again, best practice is going to be to undo those groupings. Looking ahead, I can see inside the square brackets that I have another set of brackets with an opportunity here to use distributive property, which means that the variable I'm trying to isolate, the t, will have a coefficient. It'll be multiplied by b. So at the end, I'm going to have to divide by b, likely, or I know I will, to isolate the t. So it's possible that I'll end up with some sort of complex fraction. So for that reason, and just because there's a lot going on here in terms of brackets, so in terms of groupings, I'm going to suggest that we open up brackets first. Let's have a look at the next step, therefore. We would have V is equal to, well, we'll look inside the innermost bracket first. 1 plus B times T minus B times T naught. If I had any like terms inside these brackets, I would now collect them, but I don't, because BT and B and T naught are not the same thing. So now I'll use distributive property to multiply the V naught by everything inside the brackets. V naught times 1 is just V naught. V naught times BT is B times T times V naught. I'll put them in alphabetical order this time. And finally, V naught times B times T naught is negative B, T naught, V naught. Don't lose track of what variable you're trying to isolate. Let's make sure we know where that is. Here's the t, and I've underlined the term that it's in. It's the only term that has the t, so I don't have to worry about adding, subtracting like terms, or trying to factor out the t. If it only appears in one variable, in one term, I'm just going to isolate that term. So I'll do that by subtracting v naught from both sides to move the v naught over, and by adding b and T naught V naught to both sides. So we have V minus V naught plus B T naught V naught is equal to B times T times V naught. So the only remaining problem to isolating the T is that it's being multiplied by B and V naught. So I'm going to divide by B and by V naught. Of course, I have to do the same thing to both sides. So my B's cancel and my V naughts cancel. What are we left with? Well, we've got, I'll write the t, the variable we're looking for on the left-hand side this time, is equal to V minus V naught plus B times T naught times V naught, all divided by B times V naught. Because we have 3 terms in the top, but only 1 term in the bottom, you could rewrite this as 3 fractions, which means that you could simplify some of those fractions, because each fraction would have 1 term on the top and 1 term in the bottom. But the way we've left it here is a perfectly valid answer. We've isolated variable t as was asked. Let's move on to a formula that relates Fahrenheit and Celsius. We're told that temperature in Fahrenheit is 9/5 the temperature in Celsius, and then we'll add 32. But now we want to know, what is C equal to? Let me write it here in the middle one more time. F is equal to 9/5 C plus 32. Well, our first job, of course, is to undo any groupings. But just so that we recognize the formula when it pops out, I'm going to avoid that particular piece of advice. And the other reason I'm going to do that is because I see that here's the term that the C is in. It's got the 9/5 in front of it. I can get rid of that in one go. The 32 isn't currently part of that fraction, neither is the F. So let's just try it. Maybe try it by multiplying everything through by 5 first, and we'll see if we end up in the same place. But I'm going to skip my own advice just this once. I'm going to subtract 32 from both sides to isolate the term that c is in. So I have f minus 32 is equal to 9/5 c. Okay, now I am going to get rid of the 9/5. Now remember, I'll write it on the side here, that if I have 9/5 c, that's the same as having 9c divided by 5. So how would I get rid of the 5? Well, I want to multiply both sides by 5, right? That'll allow me to cancel the 5's. How do I get rid of the 9? Since the 9 is being multiplied by c, I would divide by 9. Then the 9's cancel and the 5's cancel. So I'll apply that to the whole problem. I'll take the left side and the right side and multiply through by 5/9. So I am getting rid of the grouping, the fraction, just not in the first step this time. All right, so on the right-hand side, the 9's cancel and the 5's cancel as promised. And I'm left with c, just write it over here, is equal to 5/9 times f minus 32. So the reason I didn't multiply through by 5 first is because this is how we're used to seeing the formula for Celsius in terms of Fahrenheit. If you multiply through by 5 first, that's absolutely fine. Again, we may have slightly different answers here, but as long as we've isolated the variable and done all the mathematics correctly, we can have answers that look different, and that's just fine, as long as they're equivalent. And our final two examples. These ones have some squares in them, and again, we have in this bottom where we're looking at volume, we've got some fractions to boot. So looking at q is equal to SLD squared, we're asked to solve for d. D is sitting right there, so it's actually fairly straightforward at the beginning because I can isolate d, or at least d squared, fairly easily simply by dividing both sides by s and by l. That's its only problem. It's being multiplied by s and l, so we divide by s and l. So now I have d squared is equal to q divided by SL. But I don't want to know what d squared is equal to. I want to isolate d. Remember that if I have x squared, if I take its square root, I get just x. Why? Because taking the square root of something asks what multiplied by itself twice gives me what's under the radical. Same way that this question, the square root of 4, asks what multiplied by itself twice gives me the number under the radical. Well, the answer to that is 2. And because x times x is x squared, the square root of x squared is x. Okay, so I can isolate d squared by taking the square root of both sides. Well, here's something else I have to remember. When we talk about the square root of 4 being 2, that's correct. But it's only one of the answers. If I take the square root of something, there are always two solutions. Positive 2 times positive 2 is positive 4, but the square root of 4 could also be negative 2, because negative 2 times negative 2 is also positive 4. So to summarize these two answers, we would write the square root of 4 is equal to plus or minus 2. Again, most of the time, it's sufficient to give just 2 as our answer. We call that the principal square root. But when we're solving an equation like this, and we're not told what d is for, we don't know if that's a length, or maybe it is a value that can be negative. We want to be quite sure and give both the positive and the negative answer. So I'll clean up briefly here. And now the final answer. We have d, the square root of d squared is d, is equal to plus or minus the square root of q divided by s times l. So remember that a square root has two solutions, a cubed root has three solutions, but only one of them is a real number. So if you're taking a cubed root, you only have one real number answer. Fourth root will have four solutions, but only two of them are real numbers. So again, we have positive or negative. So we really only have to worry about positives and negatives when we're taking a square root, a fourth root, a sixth root, any even root. We can apply what we just covered in this last question. So we have v is equal to 1/3 pi r squared h, and we're asked to solve for r. This one I know for certain because we're told it's a volume of a cone, so v is for volume, and the r here, that must stand for radius. So I do know that the answer must be positive. I can't have a negative radius. So just this once, I'm going to ignore that I have two answers because I know that it's not physically possible. Okay, we have to solve for r, and what is going on here? Well, again, remember that 1/3 times pi r squared h is the same as writing 1 times pi times r squared times h. So pi r squared h divided by 3. It's just tidied up a little bit. This is the form we're more used to seeing it in. So the very first step we'll use here is, again, getting rid of the grouping, the fraction. So I'm going to take the left side and the right side and multiply both by 3. These 3's will cancel the same way as they would if I had written it in this form on the right-hand side. Okay, what do we have left? On the left-hand side, we have 3 times v, and that's equal to 1 times pi times r squared times h. R squared is in a single term, so now we're going to divide by pi and by h. Of course, we'll do the same thing to both sides. Our pi's cancel and the h's cancel. And r squared is equal to 3 times v divided by pi h. Of course, we don't want to know what r squared is. We've been asked to isolate r, so we'll take the square root of both sides as our final answer. Again, because I am absolutely certain here that the negative value has no literal meaning, has no physical meaning, I'm going to give the answer as the square root of 3v over pi h. But if you're given no other information, a good rule of thumb is to give both the positive and the negative as your solution.